Here's Johnny, the humanoid. Give a wave for the camera. 24 degrees of freedom, and I've had 4 previous streams talking about him and programming him to pick up socks and moving from there. So lots to discuss this time. Put them to the side here. I have my public Notion page where I have a plan for this 5th stream. And in the first 4 streams, I covered many different things. So in November, I received Johnny. I took some pictures and had a stream about unboxing him. In December, I had a second Twitch stream. I was showing Johnny's servos, degrees of freedom, showing how to use the PlayStation controller, the app, showing some code and all his actions that he comes with straight out of the box. In the third stream, Notion user. In the third stream, we were talking about soccer playing versus sock picking, which I found some analogies between them. You can do both with a visual servoing approach. You can do both with motion planning. Approach 1 is visual servoing. Approach 2 is this motion planning, state estimation, control. Approach 3 would be pure reinforcement learning scaled. And then approach 4, a bit hard to do it with soccer, football, but would be imitation learning. Cool. And then stream 4, I was doing simulation. If this will load. Talked about bi-bullet kinematics, everything. Anyway, let's talk about this stream. More generally, I should discuss why I'm doing this. And also like programming time versus storytelling time. So I need as much time as possible to program Johnny. He's a complicated beast, a complicated machine. Even just to pick up socks is quite a challenge. So I need 20, 30 hours a week on top of my full-time job to be programming him just to pick up socks. There's so many elements here, and I talk about all these different fields that have to come together, or different approaches to actually make, for example, even just sock picking work. But there's many different approaches, and I've made a lot of progress. So I want 20, 30 hours of programming time and then a bit of storytelling. So that includes this Twitch stream, editing them for some clips, social media, all of that. And I was editing these streams before and posting to YouTube. They were taking like 2 hours, but then the stream started going longer, and it was estimated to take 5.5 hours to edit the 4th Twitch stream. So I think I'm going to not edit them anymore and instead spend those hours, let's say the 2 to 7 hours a week on storytelling, editing clips out, creating shorter demo videos, tweeting, social media, creating slides, and eventually presenting these slides. I think that's better use of my time. And like, what is my goal here? It's like work it out as I go along. As long as I'm creating and releasing, it's better than not. Like, perfectionism is a real problem for a lot of people. Just release. Don't be like George R. Martin, who hasn't released that book for 8-10 years or so. And then why not just record not live and then edit later? I think just the live format prepares me for live storytelling, telling the story on the spot. And then I would be like trying to edit a lot. Whereas just live, I mean, we hit record and we're gone. We're recording. So I need as much time as possible to program humanoids, since it's complicated and I'm understandably lacking many skills. Like, humanoids are hard. You need teams of 50, 100 people to make these things work well. There's just so many different fields involved in humanoids like this. Otherwise, you'd have them in your home, and we'd need Will Smith to save us. Okay, so let's get straight to it. Visual sock picking. It's happening. So I have multiple different scenes in OBS Studio here. I can show some of the code, the terminal, and the camera is timing out here, so I might unplug it, which usually fixes it. Which is here. Just unplugging this USB, and plugging it back in. Don't know why that always happens with cameras across many robots I've used. Cool, and then here I'm going to go to my kickball node from stream tree. Let's get this working. Source. Oh. And then here I've renamed the script to Rust Launch Visual Servo and Grasping. I've got my cube. Let's begin with the cube instead of a sock. I'm going to put it on the table here so you can see it. And I have Orbiz. I've got this view from his camera, and I can actually drag a rectangle, this purple rectangle, around this red cube, and now we're tracking that. So the purple stays as the same pixel location, but the green is now the actually tracked rectangle you can see in the bottom left here. We're tracking this, and his head is following the red cube. Let's see if we can see his head here. The rectangle kind of changed location. Cool. I have walking disabled right now, but if I press W, he will start walking towards it. Okay, so what shall we do next? If put it here, I can move this other webcam away. A bit dangerous to have him on the table. And I'm going to press W in this OpenCV window. And he's walking. Get into position. And what a grasp. Into my hand. And that worked. So, yeah, the tracker lost as he was lifting it, but his head was following it. So, let's try to do this with a sock. There's two socks on the ground over here. I'll bring the webcam to see. Okay. Let's do the same, but this time with a sock. And you'll get the third person view this time. So there's a sock right here. Let's cover it. And he's immediately starting to walk towards it. Here I can see some text that helps me debug. We have to get to this green rectangle. That's the control target. A very shaky head. And we made it. Okay, that was a failed grasp. That's okay. Life is hard. And I think he has lost track. So let's Let's track it again. Okay, you lost track. Let's press W. Now he's not walking. I'll then move him. And let's track another sock. Again, I'll press W. We can see here the forward distance is 0.42. It's decreasing, we're getting closer. The horizontal distance, 0.2, but it's highly variable there. The error, based on where I want to actually get to this green rectangle. Okay, we're close enough. We're activating. Is it a grasp? No, but it was on target. Let's try a few more. That seems to fail. So I have to reset. The camera failed again. Let's see. Press W again. Yeah, that's the camera failing. And we're on target again. Okay, not tight enough of a grasp. Then I'm going to investigate my grasp in front. Yeah, I was doing less tight for the cube. We can try a tighter sock grip here. Let's only focus on the socks. I'm going to restart my visual servo grasping launch file. And put them in a position to walk towards the sock again. I think we would have successfully grasped the last few times there if we just had a tighter grasp. So I'm going to press W twice. And the yellow writing is the command velocities I'm controlling. 5 millimeters per second, 4 millimeters per second, and then the rotational speed, which is aggressively changing up and down as we shake the head, which is one problem I need to fix. The problem with humanoids is we have shaky heads while we're walking. Okay, here we go. Failure again. It's retrying, because it's still tracking the same object. Okay. Strange. This was working at 70% accuracy the other day. Let's keep trying. Okay, I'm going to turn off walking. That's actually not, it's another bug. Let's restart the script. And try to track and follow again. So I'll explain how all of this works in a bit, but for now I just want one successful grasp. It's getting closer. Okay, we lost track there. Maybe the camera failed. Yeah, the camera failed. And now we're tracking a random object. Cool. Let's move them again. And track this suck. Well, as we get closer, we lower the forward speed by a little bit. Okay, here we go. Oof, that was a tight thing, but it just about grabbed it. Maybe not well enough. This wasn't even a good track. Many different failure cases. Let's try again. Okay, this looks successful. Okay, that was good. So we have a success case. Okay, so I got 70% suck picking accuracy a few weeks ago, but right now this is not looking as good because of all these errors. I'm not fully sure what the problem is. But in the beginning, one problem, so like we can talk about error, failure cases, or causes. Too loose a grasp, too in grasping wrong place, camera failures, tracking failures, at least these cases. Sorry, just thinking how to proceed. I'll just discuss how the whole thing works. So I covered in other streams this kind of kickball node that now is visual servo and grasping. And typically what is done in this kind of main loop is we're asynchronously getting tracked objects, and if we have a tracked object, we set it as the target object, and then we're going to try to track it with our body, move towards the object with our body, using this new Raytrace controller, which is an improvement. And let's go to that function. I'm actually getting the head transform from the ground to the head. Let's see. Orb is here. Actually, it's not showing now because let's pick another object to track like this and turn off walking. Okay, so I had to tune the URDF file to actually make the camera link move with the head pan and tilt. And I was tuning the location so this green line comes out of it. And this is kind of a ray tracing operation to the ground, assuming that the right ankle is on the ground, which it isn't all the time. You can't see because of this camera. Let's make this a bit smaller. So the green line is coming out of the head, and using this we can actually turn the control problem into a 2D problem. How far forward is the tracked center of the bounding box, and also how much to the left and right. Even though humanoids are complicated machines with 24 degrees of freedom, they do, when they're walking, roughly live on a plane like humans, walk around. So there's like 2D locations on the ground where the sock is. And we can actually see here the red disc is 0.186 meters, so 18.5 centimeters forward compared to the ankle, right ankle link. And I want the target to be closer to 0.135, so that's what we're optimizing towards, the set point in control theory terminology. Then horizontally, I actually want, based on my current grasp, I want, given that the y-axis is pointing towards the left here, so then we actually want the target to be 3.7 centimeters to the right of the ankle pitch here. So to the right from this gray line here, 3.7 centimeters. And that target that I'm specifying is this green rectangle. But I allow some threshold. We don't have to perfectly hit 13.5 centimeters and perfectly hit 3.7 minus 3.7 centimeters. We can be within a range of 7 millimeters in forward. That's this dimension of the rectangle, and we can be 1.5 centimeters along the horizontal. So given all of this, we get an error, and if we actually end up within the threshold of both the forward and the horizontal error, then we activate the grasp. And the commanded gait manager for his walking gait, for example here, would be 0.04 meters per second. And I can actually move the sock around here, and we can see she's standing on the sock. See the forward distance go forward, of course, as I move it further away. And if I move more to the right, the horizontal distance goes more negative. Obviously, the error increases. And if I move it closer, we can actually get the horizontal error within the threshold of below 1.5 centimeters. And if I actually manually move the sock into a good position, I'm looking at Orbis here. I'm getting closer to that green rectangle. I was moving more left and noticing that's wrong, so let's move more right and down, closer. You can see parameters changing. I'm getting closer. The grasp will activate in a second. Okay, I've let go. What a grasp. Hopefully that makes sense. So that's what I am outputting to Orvis here. And the tracker is lost as we picked it up and dropped it. But it's sometimes pretty cool that the head follows the target, the object, as we're lifting it up. So let's try to do another grasp to keep trying to understand what's happening here. Let's track this sock and press W. You see how shaky that camera is. I would like to reduce the shakiness. Okay, getting very close here. The error is 0.05, and yes, we're within the threshold. We're on the green rectangle. What a grasp. Now we're succeeding. Okay, now it's not tracking anything of substance. We're still walking for some reason. So I'm turning the walking off, and it seems like I'll have to restart the script. Like when I lost track and disable walking, it seems to not actually disable. So yeah, things I want to discuss here, how the code works. I'm actually running the tracker. So let's talk about the tracker. I'm running the tracker on my local machine. So first there's the drag rectangle script, which is creating this window. We'll throw a cube over there. Place it. So that's the drag rectangle script, which is actually getting this rectangle, getting the user specified input rectangle. And we send this to the tracker. The tracker was initialized successfully, and we're now tracking live the red cube. So this is independent of any object. I can put any object, a pretty general method, as long as the user specifies the input rectangle. Can we track this as well? That's a tissue, empty tissue packet. Again, the tracker was initialized successfully. Track. I can track pretty arbitrary objects, even parts of the camera immediately died there. It's pretty annoying. I might have to replug again. Let's again show that. Yeah, we can track parts of the ground, even though they're not graspable. Camera died. See if the camera resets. Oh, and now we're actually tracking. I track the edge of this sock. That was too fast, probably camera movement. And I'd like a button to actually reset the head. Now we're like looking into our shoulder. Okay, so I'm actually running this tracker. Let's try to get to this rectangle, this sock. So we rotate a lot, even at a -8 rotation, and now we're kind of facing the correct direction. And there's a lot of noise as the head shakes around. I need to think of ways to fix that. But whatever increases the success rate. What a successful grasp. Okay, I'm going to turn the walking off. It's actually trying to pick up something. It's tracking some part of its own body there. So yeah, we have issues, lots of issues to fix, but you can see that it generally works. Okay, so I wanted to talk about the tracker. We're running the CS or T tracker actually on my laptop and not on Johnny because I wasn't able to get OpenCV Contrib working. The only trackers I had on the Raspberry Pi of Johnny were these. All of them were hard to get working. So I actually decided to track on my laptop and send images over the network to my laptop and track there. I can show the tracker node. We're doing all of this in ROS, Robot Operating System, and it takes in the initial user specified rectangle, and then we start tracking that and publishing frequently the tracked object. And I was very impressed that this was able to work first so well over the network, and secondly, actually track things even as we lift them up and drop them, and as lots of things change in the background. I could eventually change this tracker to some neural network based method, but for now this is working pretty well. So, and then I was talking about this Raytrace operation. So I'm using the direction, the axis, the red axis, the X axis of the camera link. You can turn off I've lost my displays and orders here, that's annoying. And we're back. I'm going to turn off the robot model so you can see the full TF tree of the humanoid. By the way, actually, now that we're here, we can see all the links. You can see the right ankle pitch link here. That's what I'm using to optimize where the sock target should be relative to the right ankle pitch. Not the roll length, the right ankle pitch length. You can kind of see the full TF tree of the robot here. I can actually show the PDF of the TF tree as well. The base link is at the bottom. We have a body link, and then everything else is connected. For example, the head pan, head tilt, and camera link are in a chain part of this tree. IMU link is here as well. Here's the left leg, or sorry, the left arm, shoulder, pitch to shoulder roll, to left elbow yaw, and the left gripper link. Here's the left leg, hip yaw, hip roll, hip pitch, 3 degrees of freedom in the hip, 1 in the knee, and ankle pitch, ankle roll. And similar for the right arm and the right leg. So that's a PDF representation of what you're seeing here. All the different joints and links which create a URDF of a robot. And I had to change the URDF so this camera link was in the correct place, given the head pan link's rotation and also the head tilt, how much we're looking up and down. You can see the red axis is pointing down the head tilt. So let's bring back the robot model. And given this, we're able to then ray trace down from the head to our ankle pitch. So let's look a bit how that code works. Raytrace. We're actually outputting as a marker the head ground line, and head ground intersection is the disk you're seeing. And get the transform between any 2 frames in this function. We're doing some quaternion math. You can do this in many different ways. Getting a direction of this rotation matrix. And obviously if you're looking up towards a horizon, there is no intersection, so we have a max distance. And anyway, if we're looking close enough downwards, we have to find the intersection with the ground plane. And actually, given the ankle pitch link, we're actually able to find the ground plane without doing any perception exactly. We can say if there's like a max distance, is what I was talking about. And using this, we're able to then draw this line that you're seeing from the camera link to the ground and find the intersection to the ground. I could make another link that is actually directly on the ground. It's not exactly the ground plane. It's just 2 centimeters above or so. But it's close enough for our use cases. And it's pretty accurate. I could measure the accuracy, see what other errors we have. Functions for publishing the markers, and then calculating the distances to the right foot. That's the most important thing. So you can have a Euclidean distance, that's like the yellow line you're seeing. But also there's a horizontal distance, how much left to right, and how much forward distance, how far away it is. And these are the kind of forward and horizontal distance you're seeing, and using that we can get an error metric for a controller. So that's the ray trace from head to ground. Then we have actually a ray trace approach controller that, given these distances, we can then have a gate using the Johnny's High Wonders code of the gate manager to specify how much speed to go forward and how much to rotate. And at the end, given these distances and the error, we can then create all this text that you're seeing. And at the end of the day, we're then specifying how much forward to go, how much to rotate Johnny. I'm not specifying any 0 y amplitude strafing. So I could make Johnny walk sideways. But sideways like this, and it probably would be better for some use cases, but for now it's not necessary. It's also doing some things with leg odometry. Just have one bug with that still. So if I change to the odometry frame, I was trying to then use this to see how far we travel. Let's actually control him with the keyboard maybe. Or no, let's track something. The head moved too fast there. Now, given the leg odometry, I'm actually able to see how far we have traveled in odometry. But it's a very bad leg odometry. It's just using the commanded forward and rotation and integrating this over time. I think it's not properly working right now, actually. Another successful sock pick. Cool. So yeah, this ray trace approach controller is able to then specify how much forward, how much rotation. Anyway, back to the visual servoing grasping. This body track process, we get the head transform, we calculate the ground intersection, and then given these distances, we're able to then publish some markers and then process. That's the most important function. We calculate walking commands and we send this forward speed. And eventually, if this returns true, for example, here, if the speed is set to the forward speed is actually 0 and the rotation speed is 0, that means we're close enough and it's time to grasp. So we return true, otherwise we return false. And here then I actually activate grasp in front. So on one level we're sock picking. I'm proud of Johnny. I would love to have the tracker running on the OpenCV, but eventually I want neural network trackers that can track through obstruction and occlusion. So I have to get used to cloud computing or using my laptop as a cloud computer with more heavy neural networks. And also we have this SD card, so I only have 5 gigabytes left. So to install OpenCV Contrib, you need a lot of gigabytes. But I will upgrade one day in the future to get a bigger SD card on the Raspberry Pi. Kind of bring this possible improvement section up here. And also we're not fully autonomous. Needs user input and to move Johnny every now and then. Ideally, we look around for socks, detect them. I was actually able to detect them with Dino V2, but I'll do that for another stream. Grounding Dino V2. That's for another stream. Talked about this Raytrace head camera. That aligns with the ground plane. And then that gives us this 2D horizontal X and forward, backwards, Y position on the ground, which on a proxy to the ground plane to optimize the controller towards this position. And I talked about how I changed this camera link. I can kind of open the URDF file here. Made sure that this camera link has a joint and that is actually following the head tilt. As we said, from the head tilt is connected to the head pan, so we want to make sure that this chain actually works. Before it was disconnected straight out of the box from iWonder, so I have to connect it by then specifying a joint called the camera that is attached to the head tilt link, and then camera link is the child link of the head tilt link. And I was tuning this X, Y, Z relative to the head tilt, and that's why we have such a good, just manually through trial and error, changing the position of the camera link until it was pretty much in the center of the camera. I don't know how much more I could tune that, but it's close enough. Okay, so that's sock picking is working. So let's do a January retro, February plans, and another time we can do many more things, make this fully autonomous, reduce all the errors. Okay, so January, what happened in January? I made my whole Notion page here of November, received Johnny, December, ramping up, January, and now we're in February. Happy February. So in January, my plan, sock picking through any means with an accuracy above 10%. It seems we definitely got that. I got 70% when I tried 10 times in a row, 7 out of 10. I'm going to release a video on YouTube on that. And I was saying even clicking on the screen. I tried clicking initially, but I had to drag a rectangle. That was a much better method and is the usual input for trackers. And I have a lot of work already done on this Dino V2 to find any socket, any arbitrary object. So I would give this a green completed, 7 out of 10, 70% success rate. I can try to get that to 90 or higher. Let's see. But it's a very basic visual servoing method. And how I described visual servoing before was if sock to the left, rotate left. If sock to the right, rotate right. It's a bit simplified, but generally that's how I see visual servoing. It's controllers, PIDs. And even with this method, I was able to pick up an egg cup. And you see, pick up red cubes. It's an arbitrary object method, as long as the user specifies the rectangle. And then soon Dino with a user prompt can then specify any object. Pick up the scissors, but don't run with them. I have 4 other goals that I specified as semi-completed. I did make this URDF better. I talked about this in the last stream. the URTF is more realistic and better, and I was able to do more of the same actions that Johnny can do in the real world as in the simulation. But it's really hard to tune the mechanical properties and dynamics of the URDF to make it more realistic, and I'm not sure if it's worth it. So I didn't fully achieve all my goals of building tests in simulation and actually enabling Johnny to pick up in the simulation. I don't know if it's as important. In the future, I'll be buying other humanoids probably, which will be better simulatable. I have done a lot of progress of teleoperation and motion retargeting, but I still didn't fully get there. I want to actually enable myself to be able to control Johnny with my own arms, with a camera looking at me, and enable him to pick up things so I can collect data for imitation learning. And I did actually a lot of progress with a simulated 1 degree of freedom servo with a scripted policy, and then make imitation learning train on that and seeing the limitations there. And I want to make it work on a real servo so we can point towards a target, for example. I was able to actually simulate many of his actions, all 24 degree of freedom actions. I was inputting that to an imitation learning kind of neural network, CNN. And that's what I mean by these action sequences. And then reinforcement learning, I began training, but I haven't made them stand up yet, so I need to do proper ORL empirical design there. So what are my goals? As you can see, some goals are a bit badly specified. I could get better at specifying very clearly what the goal is. And not aim as high, but I at least got lots done in every single goal here, but I didn't finish these 4 goals. So let's maybe try to be a bit more realistic in February. Also, humanoids are hard. So what are the February goals? We have sock picking working, so now I've made the goal harder. It's clutter clearing. This is a common task. It's probably one of the first home use cases. Instead of just vacuuming our floors, robots should actually move all the objects on the ground and on tables to better locations. But for now, how I define this is 5 different instances of 5 objects dropped into a container and within 15 minutes. So I'll put 5 objects on the ground, and hopefully within 15 minutes he will then bring them all, pick them all up, not drop them immediately, actually walk all the way to the container and then drop it in the container. Objects, haven't decided the 5th object, but the first 4, socks, egg cup, tissue packet, and then the red cube. As long as they all fit in his gripper with his payload. And I think I probably need a behavior tree or a state machine to look around for objects, perceive, choose object, detect failures in any part of sequence, travel to container, and probably before that I have to look for the container. But a lot of different states here. I'll probably look for the container with Dino V2 and rotate until we can find it. Could do state estimation to remember, but for now let's just stick with visual servoing. I already had look for container, travel to container. Repeating myself here. Grasp the object. Fallbacks. Drop it inside. And failure is allowed, but as long as he completes the task within 15 minutes. And he should automatically retry or know if he's failed. Yeah, and I'd like to practice these behavior trees. I'm used to state machines, but behavior trees is another way to do this kind of an application. There's pi trees, which I'd love to understand a bit more. There's often this blackboard, rapid development, medium scale, and you can then change it even dynamically in the visualization, and different things will happen. Whereas the demos. So we'll investigate that. So a sub goal that's kind of important would be to have 80% accuracy, especially if I want to get within 15 minutes. And a side goal, get it even faster. Don't want to spend too long. So within 8 minutes will be nicer. Another goal I have here is imitation learning, to pick up a specific white sock without moving legs at 80% accuracy. So this is similar to what was done with these S100 arms that are being used to pick up objects in LabRobot, for example. This is the calibration in LabRobot. It's not a specific example here. S100 imitation learn. A week ago. He's controlling it with the video. Could I do the same with a humanoid? It makes it a bit harder. Different tasks. What are you trained it for imitation learning? Pretty impressive. Is someone actually doing reinforcement learning of this same arm? I don't know if they're going to show a case of it actually working. Fine. So yeah, but the question is, how do I collect the data? Whether it's like a space mouse or sliders? Probably sliders won't work. And then the question is full teleoperation with RGB/RGBD camera. And I want to put the objects on a higher surface so I don't have to worry about them bending over to reach the objects. Part of this is to make one, again, the same goal from January, make 1 degree of freedom servo like point towards the target. It's using visual input and proving that you can change one servo to do a specific task and deal with the variation within the environment and the task. And then if you get that working, it's like the same kind of pipeline to scale to 4 degrees of freedom of an arm. I was even trying to like imitate mouse control and other actions that Johnny's doing. Again, when I get Orel to make him stand up, and teleop, I'm moving faster here, and I want to have a talk in March, so I want to get slides ready and talk for that. So teleoping would be a nice way instead of doing sliders. And yeah, that's it. Bit of a strange stream today. Was sick all week, but I'm just about recovered. So I think I've covered everything. Sock picking is working. Let's move to harder and harder challenges. Cool. Thank you.